Ever get that feeling when you're staring up at the night sky, just looking at all those stars, and you kind of realize just how massive everything is? It's
Yeah.
mind-boggling, right? But here's the thing. It's actually getting even bigger. The universe is constantly expanding.
It is, and it's not just expanding, it's accelerating. It's getting faster and faster.
Exactly. And for a long time, scientists thought, okay, after the Big Bang, gravity should be pulling everything back together, slowing it all down.
Right. Makes sense. Right.
Makes total sense.
Right.
But then they discovered something totally unexpected. That expansion isn't slowing down at all.
No.
It's speeding up.
Uh,
And the force behind this cosmic acceleration, we call it dark energy.
and it's one of the biggest mysteries in the universe. It makes up something like 70% of all the energy out there.
70%.
That's a lot.
Huge. And it acts like this, this kind of outward pressure pushing everything apart.
Pushing against gravity. Yeah.
Yeah.
Battling it out on a cosmic scale. And for years, scientists thought, okay, dark energy, it's constant, it's steady, it's always been the same.
The bedrock of our cosmological models, right?
Exactly.
This is what's known as the lambda-CDM model, right?
That's the one.
And it's been incredibly successful at explaining so much of what we see when we look out into space.
It really has. It fits the data from the cosmic microwave background, the afterglow of the Big Bang.
Right.
It helps us understand how galaxies are clustered together.
So much of the universe just makes sense in light of this model.
For nearly 3 decades, it's been our go-to framework.
Okay, so the lambda-CDM model and its constant dark energy have been doing a pretty good job. But now we have some new findings that are, well, they might be shaking things up a bit.
They might be.
And these findings are coming from a project called DSI.
DSI, yeah, the Dark Energy Spectroscopic Instrument. It's a really cool project.
What is DSI doing exactly?
So imagine the most detailed 3D map of the universe you can.
Okay, got it.
That's what DSI is trying to create. It's mapping millions of galaxies, figuring out their distances, and seeing how the universe has been expanding over time.
How does it do that?
By looking at light. As light travels through the universe, its wavelength stretches. We call this redshift.
Redshift, okay.
Like a sound getting lower pitched as it moves away.
I get it. So more redshift means further away.
Exactly.
Cool.
And by measuring this redshift, DSI can tell us how fast the universe was expanding at different points in its history.
And this is where things get really interesting, because DSI is finding something that might just completely change our understanding of dark energy.
It might.
What's the big discovery?
Well, it looks like dark energy might not have always been constant.
Really?
The evidence suggests it might have been much stronger in the early universe.
So like the universe was expanding even faster back then?
It seems that way, like the gas pedal was really pushed down.
Wow. And what's happening now?
The data indicates that the strength of dark energy has decreased gradually over time.
So it was stronger then, weaker now. That's a big change.
It is, and it has huge implications.
Now, I know scientists use a specific parameter to describe how dark energy behaves. They use the letter W for this.
That's right.
What's W all about?
You can think of W as like a dial that tells us about the pressure dark energy exerts. In the standard model, with a constant dark energy, W is always -1.
So -1 means constant pressure, constant dark energy.
Exactly. But what DSI is finding is that W wasn't always -1.
Interesting. What values are they seeing?
In the early universe, it looks like W was much lower, maybe around -1.4 or even lower.
Whoa.
But today, it's closer to -1.8.
So W is changing, which means dark energy is changing.
That's the interpretation, yes.
And this is a big deal, right? I even read a quote from Bhuvnesh Jain, a cosmologist, who said these findings have profound implications. Why is that?
Because it challenges a fundamental assumption about the universe. If dark energy isn't constant, then our basic understanding of its nature could be wrong.
Everything we thought we knew about what's driving the universe's expansion might need to be rethought.
Exactly.
That is profound. Now, it's not just DA that's finding this, right?
You're right. There are other studies pointing in the same direction.
What else is out there?
Well, when we combine DAI's data with other measurements like the cosmic microwave background, supernova observations, galaxy clustering, the picture gets even more compelling.
All these different ways of looking at the universe are telling a similar story.
They are. It's like getting independent confirmations from different sources.
And there's another project called the Dark Energy Survey, or DES, that's also seeing hints of a changing dark energy.
That's right. DES is another large-scale survey, and their findings seem to be consistent with what DAI is seeing.
So 2 independent teams, different data, different methods, same result. That makes it a lot more convincing.
It does. It adds a lot of weight to the idea that this might be a real phenomenon.
But wait, there's another side of this story, isn't there?
There is.
Some observations are still consistent with the good old constant dark energy.
That's right.
How can that be?
Well, we have observations from the Atacama Cosmology Telescope, ACT for short.
Okay.
ACT studies the cosmic microwave background, and their data seems to fit perfectly with the lambda-CDM model.
So no changing dark energy according to ACT.
Not so far. And Joe Dunkley, a researcher with ACT, has said they don't see any evidence for deviations from the standard model.
So we have some observations suggesting change, some suggesting constancy. It's a bit of a cosmic puzzle, isn't it?
Absolutely. And this is where the real fun in science begins, trying to reconcile seemingly contradictory findings.
It's the scientific process in action. New evidence challenges old assumptions. It's exciting.
It is. It keeps us on our toes.
Now let's dive into the theory side of things.
Mm-hmm.
If dark energy is changing, what does that mean for theoretical physicists?
It means a lot of head scratching and probably a few sleepless nights.
Why is it so challenging?
Because our current theories are built on the assumption that dark energy is constant. They struggle to explain why it has the value it does today, let alone why it might have been different in the past.
So it throws a wrench in the works.
Big time. And then there's this idea of phantom dark energy.
Phantom dark energy. Sounds spooky. What is that?
It's a scenario where that parameter we talked about, W, is less than 1 to 1.
Right, W, the pressure dial.
Exactly. If W is less than 1 in quant, it means dark energy strength actually increases as the universe expands.
Increases. Shouldn't it be getting weaker as things spread out?
You'd think so, right? But phantom dark energy flips the script.
And that's a problem for our theories.
Huge problem. It messes with some fundamental ideas about energy. It leads to some very strange and potentially catastrophic predictions.
Catastrophic, like what?
Well, one possibility is something called the Big Rip.
The Big Rip? That doesn't sound good.
It's not. It's a hypothetical event where dark energy becomes so strong that it literally rips apart everything. Galaxies, stars, even atoms.
So the universe ends not with a bang, but with a rip.
Yeah, that's the idea.
Wild.
But remember, it's just a theoretical possibility at this point.
Hopefully a very, very distant possibility.
Let's hope so. But yeah, these findings, especially the idea that W might have been significantly less than a -1 in the past, are a real challenge for theorists.
And I saw a quote from Seshadri Nadathur from the DAS team, who said that while it's difficult for theorists, he hopes the evidence will be convincing enough for them to adapt their models.
It's a hopeful perspective.
It is. It's this interplay between observation and theory that drives scientific progress.
Absolutely. And the story of dark energy is far from over.
What does the future hold for dark energy research? What's coming up next?
The next few years are going to be incredibly exciting.
Why is that?
Because we have a whole bunch of new instruments and telescopes coming online that are going to revolutionize our understanding of dark energy.
Like what?
Well, DSI still has a couple more years of observations left, which will give us even more precise data.
Great. What else?
We have the Euclid Space Telescope. It just launched, and it's going to be mapping billions of galaxies, giving us a super detailed view of the universe's structure and expansion.
Billions of galaxies. That's incredible.
It is. And then there's the Vera C. Rubin Observatory. It's going to be starting its legacy survey of space and time next year, and it'll be scanning the sky every few nights, creating a kind of movie of the universe.
That sounds amazing.
It is. And it'll be perfect for studying things that change over time, like, well, maybe dark energy.
So much data.
And then in 2027, we have NASA's Nancy Grace Roman Telescope launching.
Another space telescope.
Yes, and it's specifically designed to study dark energy and exoplanets with incredible precision.
Alexei Lifaud-Harned said it's going to be a golden age for dark energy theorists, and I can see why.
I agree. With all this data coming in, we're going to be able to really put our theories to the test and hopefully solve some of the mysteries surrounding dark energy.
Maybe even figure out if it's changing or not.
Exactly.
Now let's bring it all back to you, our listener. What have we learned in this deep dive?
Well, we know that dark energy is this mysterious force causing the universe to expand at an accelerating rate.
Right. The universe is getting bigger, and it's getting bigger faster.
And for decades, we thought dark energy was constant.
That W, that pressure dial, was set at -1.
But new evidence from DSI, supported by other surveys like DES, is suggesting that dark energy might not be constant after all.
That maybe it was stronger in the early universe and has been weakening over time.
That W might not always have been -1.
But we also have observations like those from ACT, which still support the idea of a constant dark energy.
So it's a puzzle. We have conflicting pieces of evidence, and scientists are working hard to figure out what it all means.
And if it turns out that dark energy is indeed changing, the implications are huge.
They are. It means we have to rethink our models of the universe.
Rethink what's driving the expansion, rethink the fate of the universe.
It could point to new physics beyond our current understanding.
And that's the beauty of science, isn't it?
It is.
It's always evolving, always questioning, always seeking deeper understanding.
Always searching for answers.
So here's a final thought for you to ponder, listener. If dark energy is changing, what does that mean for the ultimate fate of the universe? Will it keep expanding forever? Will it eventually collapse back in on itself?
Or will something even stranger happen?
And how does this changing dark energy affect other fundamental forces and phenomena in the universe? These are big questions.
Big questions with no easy answers.
But the quest for those answers is what makes cosmology so captivating.
It's a journey of discovery, and we're all along for the ride.
So keep looking up at the stars, listener, and keep wondering. Who knows what amazing secrets the universe will reveal next?
It's an exciting time to be alive, and an even more exciting time to be exploring the cosmos.